Sure. I hope you can see my slides okay. Um, so I'm going to introduce the technology and actually go through a kind of a broad spectrum of possible applications, while Ben is going to focus on Titan as a potential target, or icy moons in general. Um, and actually, Francis has given a nice introduction because, of course, miniaturizing instruments is key to take advantage of solar sail technology. It's speed rather than mass, which is of the essence here. And the instruments that we're developing are miniaturizing as far as possible while keeping the performance at levels which is going to really reveal interesting science. And here you can see the basis of what our dynamics measuring system is. And although we have used it as seismometers, so you can think of it as accelerometers, you can really think of it as providing a sense of touch for a spacecraft, even if it's touch at a distance, if it's gravity at a distance. And yeah, just to describe what you're looking at, this is the heart of the system. It's a silicon a seismic sensor. You can see a proof mass on a spring. This is all carved out of a single piece of silicon. This is the most compact, highest sensitivity sensor that is currently available. It's simple to operate. It is self-leveling, and it can measure dynamics in a very wide variety of environments. And I'll just describe a few of those on the way before Ben focuses on one of them. And the sensitivity that we're achieving at the moment, and we actually hope to improve this by up to an order of magnitude, but at the moment we're at 0.25 nanoGs sensitivity. And just to give you a view of what 0.25 nanoGs represents, apart from a lot of zeros per point before the 2.5, here is 1G, and that's the gravitational acceleration on the surface of the Earth. 0.25 nanoG is the gravitational acceleration on the surface of an apple. So we're going way down, and at this level of sensitivity, you really are sensing everything. And I want to emphasize the kind of the broadband applicability of it. So this is actually we've got 3 of these sensors up on Mars at the moment, measuring Mars quakes. But during the development of these, we were doing testing at Oxford. And here's about 3 days over a weekend. And this is a spectrogram. So you kind of read this like music, low frequencies at the bottom, high frequencies at the top, and the hour ticks are along the bottom. And in fact, during this weekend, we had 2 teleseismic events, earthquakes coming in from the other side of the Earth, one from Chile, one from Indonesia, a 6.8 from Chile, 6.6 from Indonesia. You can see the clear signature here. And inside of here are surface waves that Ben will be talking about. You can also see the ocean. This is actually the coupling of the ocean of the Earth, which peaks at an energy injected in this bandwidth. There are quiet periods below this. In fact, we get down to the sensor noise. But also we noticed on Sunday, and you can just about see it here, but if we zoom in, I think it'd be more obvious. You can see that there were distinct signatures that were coming in on Sunday, and this is expanding the frequency range. This is from 1 to 3 hertz, but generally we're looking from 1,000 seconds up to 100 samples per second. So it's a very broad range, a broadband instrument from that point of view. So here you can see these seismic signals, and we've only got one sensor, but we've got 3 axes on it, and we can see where these signals are coming from. And this is actually a color coding depending on the azimuth, where the energy is coming from. And from this, we could actually see that what we are looking at here are the bells. In fact, this was testing into the physics department at Oxford. And during that Sunday, it was in fact a Remembrance Sunday. So you can see the bells on the 11th of November, or it was the nearest Sunday, being tolled both before and after 11 o'clock in the morning from St. Giles, Merton, Christchurch, New College. And the fact that in one spectrum, you can get information from just a few hundred meters away and the other side of the world shows you just what you gain from such a sensor in terms of a broad spectrum scientific observation. So I want to now just show what we saw on Mars, and this very briefly, this is a Mars quake on as detected by the silicon sensor. In fact, this is the vertical axis, and you can see a strong excitation. In fact, this is a conventional P wave, and then the S wave coming along, and we're now breaking that down and getting out a cross section through Mars using this sort of using the source of seismic analysis. In fact, working with Francis on this, that we use on Earth, we're now applying this to Mars for the first time. But also I wanted to go back to some of the data we got even before we landed. This is on the cruise to Mars. This is data on the right-hand side. And you can see during the cruise, this is the actual spacecraft, we use attitude control thrusters that give little course corrections. These are running all of the time. You've got here about 5 hours of data picked up on 2 sensors. So it's a kind of time on one axis and then an acceleration that is being picked up on these sensors on the other, on a 2-dimensional plane. And you can see the thrusters firing regularly, and each of them, there's 4 of them that fire in various combinations, and these are being picked up. Lockheed Martin were fascinated by this because it's the first time they actually saw the dynamics of these spacecraft thrusters in action. I mean, they see them in overall, the integrated results as from the star trackers, but they don't see them actually pushing the spacecraft onto a different trajectory, as we can see here. This is actually the residual, if you take off the thrusters from the 2 sensors that were running, showing that the overall drift here is the order of a few nanogs, but this is over a very long period of time. And this kind of begs the question, if we were doing a extra solar system mission, and we're traveling at a large fraction of the velocity of light, you can actually work out from the interstellar particles, instead of thrusters coming in and producing a signal, what will those particles do? And so this is a calculation actually just taking the particle diameter with the density that we would expect of interstellar dust, looking at the particle diameter. This is just between 100 nanometers and 1,000 nanometers, or 1 micron. And the acceleration ranges from 1 nanog up to 1,000 nanog. So this, in terms of our sensor, these are all very big signals. In fact, this is a 200 nanometer particle. This is a synthesized synthetic signal from a 200 nanometer particle hitting a solar sail at 0.2 of the speed of light. And you can see a very significant signal that we would be able to detect. And you can see this as potentially as part of an engineering a suite that could be used during cruise to see what is being hit, what you are hitting, and what damage might be happening. So just to sum up on the section here, you can look at the seismometer as producing an exquisite sense of touch to a spacecraft as a strap-on instrument. So this would be as a direct sensing of thrust, dust impacts, also flyby gravity, although we have to take into account Francis's point that the faster you go by, the less the effect will be of any gravity of an object, but also on a drop-off package, and this is where Ben will talk of this a little bit more, for instance, dropping into Titan with a high lander, maybe dropping a set of these into the eye of Jupiter to look at the dynamics as a sounder, an atmospheric sounder, or as an asteroid catch-up, where you'd actually maybe to be able to do a slow speed enough approach to be able to drop off at relatively low impact velocity a package. But at this point, I'd like to hand it over to Ben to talk a little bit more about how we would go about this in a use case for Titan.
So thanks, Tom, and actually thanks for that great introduction to this topic. And I'm just going to present to you a single potential use case for the sensors that Tom has talked about. So we know that they work very well as accelerometers in space. We know they work very well as seismometers on Mars. But there are many sort of other potential applications for deploying these sorts of things through the solar system. And I'm just going to pick one, which is a personal favorite, to try and illustrate why it would be a useful thing to try and use a sundiver mission to gather seismic data from somewhere like Titan. So as we've all heard over the last few talks, these icy moons are a really interesting target for understanding potential habitability and or the existence of life elsewhere in the solar system. In addition to that, they also provide a really interesting insight into the evolution both of the giant planets, but also of the moons themselves. And they have a structure which is in some ways quite Earth-like, but in some ways very different as well. So this is a little mock-up of Titan. And you're sort of looking at a solid ice crust on the surface with a very complicated sort of hydrosphere cycle, but methane and ethane rather than water, and a thick overlying atmosphere on top of the ice, and then probably a liquid water ocean, some high pressure ice phases, and then a sort of silicate core that extends the rest of the way through the moon's diameter. So you might wonder sort of what's the interest, what's the need for using seismology to study these processes? Well, as Tom mentioned, it's one of very few geophysical techniques that will give you information on what's 10 meters away, almost as well as it will give you information on what's 100 meters away and 1,000 kilometers away. And somewhere like Titan, or indeed any of the other icy moons, is particularly exciting because you have lots of different sources of seismic signal. On Mars, it's actually a little bit dull. You have impact events, you have tectonic events, and then you have the wind. On an icy moon, you'll probably have impact events, tectonic events, the wind, the motion of any surface fluids, the motion of any subsurface fluids, and then, of course, any of the tidal dissipation that's causing tectonic events below the water, which will be quite different to those that are in the crust. And the advantage of having all these different sorts of seismic sources means that you can use a single sensor to study all of these different aspects of icy moon dynamics, behavior, and evolution. So if you wanted, for example, to understand the nutrient flux coming up from below the surface of the ocean, if you wanted to look at things like nitrates coming through, it would be really interesting to understand the behavior of the ocean, and seismology can let you do that. If you wanted to understand how much tidal energy is being dissipated into the icy crust at the surface, to understand, for example, how much exchange there is between the atmosphere and lower down, again, seismology can help you to do that because you have lots of different seismic waves that are sensitive to all of these different areas of the moons in different ways. So in terms of the science, as we mentioned, we've had one of these on Mars for the last 3 or 4 years, and it's functioned pretty well. Again, we've managed to detect a whole host of events and demonstrated that something which is only about this big and weighs significantly less than a kilogram can provide all sorts of information on interior structure. So that combination of being miniaturized, having relatively low power, and being able to give you a huge amount of information on lots of different aspects of planetary behavior makes it a good target for inclusion on any other sort of mission. So this is just an example. We've been doing a field test with one of these out on the Brunt ice shelf in Antarctica. So what we're looking at here is sort of testing for an icy moon environment, but also looking to study the behavior of the ice sheet itself. So it's breaking up very fast in response to climate change. Not only can the sensor tell you about, say, the deep structure of the Earth, you can also use it to study very, very near surface processes and behaviors. And it's just sort of, we haven't got the data back from this yet, but again, being able to show that it can be deployed in very robust and very hostile environments without having to compromise on performance. In terms of, why a sundiver, as Tom mentioned, the advantage here is speed. So you can get somewhere very quickly, and this is not a particularly large sensor, so it's not like you would need an enormous amount of mass or power to power it. The advantage of somewhere like an icy moon is that you wouldn't necessarily need to do very much active deceleration. Slowing down for intercepts is obviously very difficult, especially if you have something very hard, something sort of very complex like a mass spectrometer. It's not going to appreciate surface impact at kilometers per second. But somewhere like Titan, you could probably get more than enough atmospheric deceleration using simple passive means like this image you can see here of Deep Space 2, which was a penetrometer that was designed in the late 90s for Mars. Mars's atmosphere is probably less than 1,000th of the thickness of that of Titan. So again, slowing down becomes much more straightforward. And I don't know if Tom will want to talk more about this, but the seismometer has actually been tested up to a deceleration of about 14,000 G. So you can fill basically the cavities inside it with a sort of resin or something that will sublimate away after landing. But it means you can survive very hard impacts without having to worry about the same sorts of delicate sort of precisions being maintained as you would for many other instruments. And again, here's somewhere where there's a real advantage to sending multiple spacecraft. 2 hitting the surface and 1 flying by to relay the data would be a really great way of being able to get measurements at multiple points in space and in time, which you could then use to make much more detailed studies of the interior structure than we can manage on Mars, where we're constrained to having only a single station. That's all I wanted to say. I hope you found that a relatively interesting sort of tidbit of talk on why we think that these seismometers are an excellent instrument for inclusion on an outer solar system mission, both one that might want to actually make a hard impact on an icy moon or a giant planet, or just for putting on the spacecraft to monitor its performance and indeed study the behavior of both interstellar and perhaps interplanetary and perhaps even later on interstellar dust properties in a way that actually would enable you to do that with a very, very small and very sensitive instrument. Thank you.